Thank you for joining the Hydrogen Energy Center and Valerity for our fourth in a series of hydrogen sessions. We are pleased today to bring you a discussion about hydrogen pipelines and hydrogen to the home. Please use the chat function for submitting questions anytime during this session. And we are certainly welcome to answer any questions you may have after the session is over. So without further ado, I think we can launch into this today's presentation. Okay, hold on a second. Well, it's in scroll mode. Okay. Today's agenda will provide an update on the Hydrogen Energy Center and Valerity, our sponsors for today's session. We will also provide a very brief update on some of the more momentous hydrogen news in the last week. The session itself is going to review the industry drivers for hydrogen pipelines and hydrogen to the home. And then we'll look at some case studies of hydrogen pipelines and hydrogen to the home, and then have question and answer. HEC is a professional association founded perhaps 25 years ago as a looking at hydrogen as an enabling technology for accelerating a renewable energy and sustainable future a little before its time. We welcome new members, are pleased that a number of folks have been joining in the past few weeks, and we are focused on sharing information about hydrogen and the industry, and also participating in legislative activities in terms of policy, as well as engaging in specific projects surrounding hydrogen, both in terms of understanding market opportunities as well as project implementation. The upcoming hydrogen sessions next week will have power generation with hydrogen. Following that, we'll look at the global trade in hydrogen, which is a fast developing market. We'll have a technical session that looks at all the means by which water can be split into hydrogen and oxygen. And we'll also look at blue hydrogen production, and that is a major industry focus as well, with the existing petrochemical companies interested in converting steam methane reforming systems to be carbon neutral through carbon separation and sequestration. Current hydrogen market is about 115 million tons a year right now, so it's a fairly sizable market with fairly significant carbon emissions that need to be addressed. And then at the end of June, we'll look at the role that hydrogen plays in the wind industry. Valerity provides management consulting services to companies involved in energy and technology, helping identify market opportunities, establish strategies, and implement action plans. Recent work has focused on the gas industry as well as the renewable gas market. Illustrative clients span the gamut of energy and technology companies. So today's session, we look at the industry drivers that are causing an interest in converting pipelines to run hydrogen and to consider hydrogen as a renewable gas for heating homes and businesses and providing feedstock to industrial and petrochemical processes. The electricity generation, the red line on this chart, you can see has gone down significantly since about 2008. And now the attention is turning to other economic sectors in the United States. You can see the green line with transportation is now the leading emitter of carbon, and that it has gone up in the last 10 years. And you can also see the light purple line, industry, with a significant emissions challenge. So attention is shifting. 24 states have legislated carbon objectives, various dates, most of them including 2050 and intermediate years as well. And those economy-wide targets for carbon reduction are core drivers of the efforts to decarbonize our economy. The electrify everything strategy is potentially problematic, and there are several ancillary activities that are associated with that. I recently heard an estimate that curtailed power could reach 25% of all power generation if we go to a full wind and solar economy. Right now, it's fairly high. It's about enough electricity in California is curtailed to provide electricity to probably 500,000 homes every year. Significant curtailment, growing every year at about 50 to 60%. The other challenge is multi-day winter heating loads may overwhelm the electricity system if we convert all the fuel-based heating to electricity-based, even with the higher efficiency air source and ground source heat pump systems. The storage strategy is problematic if the focus is on lithium ion, only because the cost, it would be very high to do multi-day storage, much less seasonal storage. And then there are certain applications which are challenging from an electrification perspective. Older buildings, dense urban areas, and city centers may not lend themselves to the electrification pathway. And finally, we're seeing a fairly significant transition in transportation with the heavy transport vehicles. And we can include in this trains, planes, trucks, and ships. To illustrate one of the challenges of an all electrification strategy, this is a chart of the daily gas and electric use in Great Britain. And you can see in the winter load, the blue lines going up and down. And the red squiggly line down near the bottom of the chart is the electricity demand. And this is all expressed in a terawatt hours, which is a common unit, which is used in Europe for describing energy flows, common denominator. So you can see that if we went to an all electric system, it would have to increase the peak demand by a large factor, a factor of 4 or 5 times, in order to meet the thermal load required in the middle of winter in Great Britain. So this is slightly problematic, especially if everybody comes online at once in terms of heating load. Now, there are ways to mitigate that, certainly, and electricity will cover a large part of that territory, but the economics will require a fuel-based solution in complementary form between the electric and the gas side to achieve both system resilience as well as good economics. The applications for hydrogen in a decarbonized society are quite varied and broad. Certainly, long duration storage is a key element, and that is what we're seeing in terms of Mitsubishi Power putting in place a relationship with Texas Brine to build salt brine storage of salt cavern storage of hydrogen throughout the southeastern United States and south central United States, which is a long duration seasonal storage of hydrogen in order to complement the variable renewable energy that's going to be on the system. We also see hydrogen playing a role in decarbonizing natural gas, decarbonizing the molecule, so-called. There are several steel manufacturing plants which are looking at direct reduction of iron with hydrogen for steel manufacturing. And as I mentioned earlier, heavy transport is moving ahead with hydrogen applications from a decarbonization perspective. The existing hydrogen usage in industry is dominated by ammonia manufacture and petroleum refining. And we're seeing quite a bit of activity in generating green hydrogen for manufacturing ammonia and decarbonizing that. And then the second part of that is that people are exploring using ammonia, for example, as a fuel in ships, as well as ammonia as a carrier for hydrogen, being able, for example, to convert hydrogen to ammonia and then ship that ammonia around the world in large tankers, and then to either use that ammonia for power generation directly into a turbine, a gas turbine, or to take that ammonia and turn it back into hydrogen and use that in a refueling strategy. The other application we're seeing develop for hydrogen is combined heat and power. We'll talk a little bit later about a project in Greece that is proposed that is using a high temperature fuel cell, and the fuel cell will provide electricity as well as heat in a district energy system that already exists, and they're interested in converting it to hydrogen. And then finally, integrating hydrogen into natural gas pipelines, as well as generating synthetic methane with biogenic sources of carbon dioxide, further reducing greenhouse gas emissions and injecting that resulting synthetic methane into natural gas pipelines. The United Kingdom has moved ahead in terms of trying to understand the decarbonization of their economy, and has done quite a bit of work in terms of trying to understand what the implications and requirements are associated with this significant decarbonization. As you can see, they've identified a net zero by 2050 and a 78% reduction by 2035, halfway between now and 2050. 85% of the homes, roughly 20 million homes in the UK, are heated with natural gas. And so the real question is, apparently that natural gas is responsible for a quarter of the emissions in Great Britain. And so it becomes a key target for emissions reduction. And the key question is, how do you do it? They've already announced that new homes will not be able to have gas and oil furnaces after 2025. Currently, there are 1.7 million oil and gas furnaces installed every year. So interesting transition. And the government has an ambition to reach 600,000 heat pump installs for residential heat every year going forward. You can see the estimated peak domestic heat of 170 gigawatts and the average estimated heat load of 50 gigawatts. So this is the ambition in the United Kingdom, and they haven't answered all the questions yet, but they've been making an effort to understand the situation. They've conducted a number of studies, and these are paper studies indeed, but they also are integrated with extensive modeling of different pathways to understand what the great energy transformation means for getting to net zero by 2050. This is one. I'll quickly review 3 papers of import in the UK. One is Clean Growth Transforming Heating. And the first sort of set of recommendations is to consider to expand investment in heat networks, district energy systems as it goes forward, to make sure the government provides, it not only provides incentives, but expands the existing set of incentives to expand heat networks in the UK. The renewable heat continue to support residential incentives. You can see the list: heat pumps, biomass boilers, solar water heaters, biomethane going forward. They also want to make sure, this is one of the issues in all of these studies, which is how do you deal with the complexity of all of these heat sources, stakeholders. So the first recommendation, make sure that there's financial support for consumers. If they have to switch out all of their appliances, who's going to pay for that? Are they going to pay for that? Is it a social cost that needs to be supported? Or are there alternatives to switching out all of the appliances, for example? Make sure that the investment and support is cost effective. In other words, have some kind of criteria for the societal impact costs of these programs. And this one of these final points in many of these studies is dealing with the uncertainties and recognizing that there are going to be new solutions, new technologies, circumstances are going to change. And so the process of setting priorities has to be dynamic and enable sort of fluidity. And that might mean at the outset, not necessarily shutting out any potential solution, but making sure that there are multiple horses crossing the stream, as it were. The final point is key, of course, which is make sure all the stakeholders have information they need to make good and effective decisions going forward. Two other reports: analysis of alternative UK heat decarbonization pathways and next steps for UK heat policy. Certainly compare the whole system costs of alternative scenarios and understand the implications of those scenarios and pathways on the gas and electric networks. This is a very complex question to answer, which is the interplay between going all electric or moving towards renewable gas or some mixture of the two. There even are hybrid boilers out there. In the UK, we call them furnaces, they call them boilers. So there are actually boilers that are going in that are combos, both gas and electric, and that they can also be combo hydrogen and electric as well. So being able to build some of the uncertainty into the capability of the end use appliances is clearly part of the strategy of the contractors and equipment suppliers. So the next steps for UK heat policy study, 3 central pathways: greening the gas supply, shifting to low carbon hydrogen, and there's a lot more complexity that's underlying that single line. Certainly electrification of heat supported by low carbon gas, and then hybrid solutions with the bulk of heat requirements satisfied with electric, and then being able to hit the peaks with green hydrogen gas or renewable methane. I have the results of 2 studies that have been done, and these are very large studies that have a lot to them, and so they can't possibly be represented in a single chart. But this shows the running of multiple models, and they had several different hydrogen strategies, several different electric strategies, and then hybrid, meaning that they were both hydrogen and electric studies. And, you know, at the end of the day, the lowest cost strategy was the hybrid set. But this begins to speak to potentially not riding the hydrogen horse entirely or riding the electric horse entirely, but hybrid, which provides a balance. But you can also shift gears if needed to emphasize certain strategies over others as new capabilities and learnings emerge. It also speaks that there is certainly a certain amount of uncertainty in these models, or the results that can be interpreted. This is another strategy of modeling by National Grid and their heat pathways. And in this particular one, I know this chart is a little bit complex, and you're free to download this after the presentation, after it gets posted on our website. In this particular case, that the hydrogen pathway delivered the lowest annual cost going forward. But again, there are assumptions, and there's certainly many options. You can see the black bars represent the variability, and that kind of uncertainty needs to be brought into the decisions as well. If we look at these charts, what they are looking at is the total cost over, say, 20 years of each of these scenarios. And total costs of each of these scenarios over 20 years normalized to an annualized cost. It's almost like a levelized cost of energy type basis to enable comparability. Now, it is important, everyone in the hydrogen industry, to recognize that if decarbonization is a critical move, we can start fresh by developing green hydrogen and blue hydrogen resources that are low to zero carbon. But it's also important to recognize that we currently produce about 115 million tons a year of hydrogen right now, the bulk of which is gray hydrogen. And certainly can see some of the petroleum and petrochemical industry players moving to carbon separation and sequestration in order to just look at the incremental cost of addressing the carbon emissions of existing systems. We can also see that the bulk of hydrogen goes to refining and ammonia, and methanol production is another application. And then there are a range of other uses for hydrogen. Most of this is in the fence production and use. In other words, there's a steam methane plant that would be located or co-located with a petrochemical facility. There also are pipelines. There's about 1,600 miles of pipeline in the United States today. And those pipelines are designed to transit hydrogen to the various points at which its use are demanded, and that's for both ammonia manufacturing and refining. Our most significant pipeline is in the Louisiana, Texas Gulf Coast area, and it has multiple sources of hydrogen onto the pipeline and multiple uses off of that pipeline. It's a very cost-effective way to move hydrogen around. Now, again, this is a chart which is quite detailed, so I will welcome your taking a closer look after this presentation. But basically, let me just explain what's on the left and what's on the right, and I can color code it for you. The bottom left is blue, and that's hydrogen production. And that hydrogen production is through electrolysis as well as blue hydrogen. And so slightly to the left of that blue block on the lower left, you can see the blue hydrogen piece and the green hydrogen piece ramping up significantly. It fairly shows what the circumstances today. We really don't produce much green or blue hydrogen. And the expectation is by 2050 that we will be producing a very significant share. Estimates of increases in hydrogen production are anywhere from 50% to multiples of hundreds percent, depending on the scenarios that are chosen. Above the hydrogen block, sort of on the middle left of this chart, is green methane production, sustainable methane, renewable methane. And that is produced both by capturing biogenic sources of methane that are out there from landfills and agricultural waste and so on, as well as capturing existing CO2 emissions and converting those CO2 emissions into more methane using green hydrogen and creating what some are calling renewable methane or synthetic methane. Then onto the demand side, with the right side of this chart, we can see that there's a block for buildings at the top, industries, the second one down, and the very bottom, we can see transportation as well, and certainly power production. And power production, we'll talk about that next week, and that's a fascinating topic. But we can see that there's a potential role for hydrogen in all of these industries, as well as a mix between hydrogen used from a blue and a green perspective, as well as hydrogen used in methanation to produce renewable methane for the system. The value chain of hydrogen is quite diverse and mixed. We can see that there are many different low carbon hydrogen sources. There are multiple means by which hydrogen can be processed. And then hydrogen transport is another whole topic of great interest, as well as the wide range of illustrative hydrogen uses. And the economics of hydrogen are challenging, depending on how much you need and in what form it takes, and certainly how you produce it. And that's why we can see in the green hydrogen industry, there's been a huge effort over a number of years for companies to establish the means by which they will get their hands on green hydrogen and how they will get that hydrogen to the place where it's needed in the quality and the quantity that's required. And it's a very challenging. If we look at Nikola and their fueling strategy, which we reviewed 2 weeks ago, we can see that they've been making an effort to establish that strategy for 3 or 4 years, and they only recently have arrived at a strategy which includes Arizona Public Service providing 3.7 cents electricity that then turns into $1.20 per kilogram hydrogen, and then to liquefy that and use liquid hydrogen transport to provide that hydrogen to refueling stations throughout the southwestern United States. Plug Power is taking a similar strategy with large-scale renewables, with Brookfield Renewables, and using that to liquefy hydrogen and transport it. And the reason they've chosen those pathways and those approaches is it delivers the cost that they need in order for their business models to move forward. And those efforts have been going on. They're not easy. And this is a key challenge in the industry, which is very careful lining up of the source, the distribution, and the point of use for hydrogen. In the heating realm, the strategies that are emerging, mostly in Europe, around decarbonization of building heat is certainly, as Amory Lovins would emphasize, that you need to make all applications more efficient if you can. And so you begin with building efficiency, appliance efficiency, energy management. And this is part and parcel of the strategies that are being deployed in the UK, from which this information is based. We can also see that the efforts are being made to reduce the carbon intensity of the supply of heat energy. And, biomethane is one, power to methane, hydrogen blending, 100% hydrogen, and then the heat networks. And certainly with a higher proportion of denser city centers in Europe and existing district energy systems, there's a great interest in certainly having the heat networks scavenge any sources of heat in their systems, as well as putting in geothermal heat pumps and air source heat pumps on those networks. But then, of course, integrating the potential for using biomethane and hydrogen in the renewable gas systems in order to provide heat to those heat networks. The range of end uses, the appliances that are being used, we can see air source heat pumps. Everyone knows what those are, and they've been improving significantly. Ground source heat pumps, which are making their way forward in the marketplace. One area which we haven't heard a lot of in the United States, there actually has been an announcement for a very significant river source heat pump in the East River in New York. I think to supply heat for I think several thousand apartments in New York City. And that's a fairly innovative use that's being applied across Europe. Yeah. We're seeing hybrid gas electric heat pumps, which is when the heat pump is operating in a very low outdoor temperature regime, the efficiency goes down. And so the electric demand goes up. And so if you don't want a coincident high demand on electricity networks in the middle of winter, if you put in a hybrid system, it can kick back to using gas networks to provide the heat in combination with the heat pump systems. Somewhat of an innovative way to address some of these peak demand issues. I haven't seen a lot of discussion on the thermal energy storage. I think we will see that emerge as we go forward, and that would be an in-house or in-apartment thermal energy storage system. We'll speak to hydrogen boilers a little bit later in the presentation as well, and we are seeing micro CHP, combined heat and power systems going in. So one system that I want to speak to is a proposed 25,000-mile hydrogen pipeline network in 21 European countries. This is just an astounding vision. What is key here is they're really talking about repurposing existing natural gas pipelines for about 2/3 of this 25,000-mile network, and then adding, new pipeline extensions into key market areas, industrial zones, etc., for hydrogen, and certainly envisioning that that hydrogen is going to be fed across the European economy most efficiently through pipelines, as opposed to using, uh, liquid trucks or whatever other methods. Well, gaseous or liquid are the only other two means by which to transport it. And so it's a fairly aggressive perspective. Uh, this is an image of the pipeline plan that has been developed. And so these ideas are not, just off the cuff sort of conceptual ideas. There's been a fair amount of work to develop the specifics around the economics and the requirements associated with building these systems out. We'll see how this unfolds going forward. And what's also interesting is that this actually was built upon individual sort of company collaborations that identified specific areas for hydrogen pipeline development, mostly in terms of connecting wind-sourced hydrogen into industrial zones, and then looking at industrial zones from a regional perspective, and then building on those initial plans, as you can see. Oh, and one other point that I do want to make sure that we touch on here, which is a key part of this strategy. The role of hydrogen in terms of modulating and mitigating the variability of wind and solar is really a key role, and that's a major driver of these systems. This includes storage of hydrogen in order to provide that month-to-month and seasonal type storage in order to mitigate the ups and downs of the energy flows associated with variable renewable energy. As we get to 50, 60, 70% wind and solar, those are all must-take resources, and there will be a significant amount of curtailment, and it creates an opportunity to turn those stranded electrons into very cost-effective hydrogen, and then to use the market arbitrage opportunity that the long-duration storage of hydrogen provides. Yes, the turnaround efficiency is not so great, but the arbitrage will be quite significant if you're buying at zero rates in terms of sourcing electricity for hydrogen production, and then you're able to sell it out at 12 cents or 15 cents a kilowatt hour during the high demand times. That is a very marked arbitrage opportunity that can be capitalized on. The other project I want to mention, I really just want to mention this because of the phased approach that they're taking. And that phased approach represents some fairly good thinking on the part of the partners, Gasunie, TenneT, and Thyssen Gas, for this project. They're envisioning a 100-megawatt power to gas facility in a industrial zone, Lower Saxony, located to take advantage of the landing sites for electric trunks associated with the North Sea wind plants, as well as access to gas infrastructure. And it's envisioned that there'll be, by 2035, 23 gigawatts of wind commissioned in the North Sea area that would be landing near this location. And again, that 23 gigawatts of wind is going to create an oversupply of electricity, creating the opportunity to convert it to hydrogen cost effectively. And they're also envisioning different stages. Let me show what we're talking about here. The stages or phases, as they're explained here, is to begin by blending hydrogen into existing natural gas pipelines, and blending up to 20% by volume means that you're going to have 80% by volume natural gas and 20% by volume hydrogen. Just a reminder for everybody that hydrogen at 20% of the volume in a pipeline, it only will represent 7% of the energy. It's not that dense at the same pressure from an energy perspective. And they will also be using that hydrogen for refueling centers for trucks. So that's phase 1 and 2. The second phase is to generate renewable methane and green hydrogen combined with CO2 for methanation. So sort of a double whammy here. Find biogenic sources of methane, landfills, wastewater treatment plants, agricultural waste, but also upgrade the errant CO2 and create additional methane and inject that green methane into the natural gas pipelines. And phase 4 is to integrate hydrogen storage with salt caverns, potentially. And then finally, in phase 5, to completely convert the pipelines to 100% hydrogen. And it's a much more integrated pipeline system that's fully decarbonized. Clearly a multi-decade approach. I want to pay attention to the clock here, but we have this case study and then another one, and then we'll open for questions and answer. I did want to point out this project for the Macedonian, sort of the northwest part of Greece. It's a $10 billion program to convert the existing 4 major coal power plants that provide 20% of the capacity in the Greek electricity system, convert those coal power plants to hydrogen. And it's a multi-pronged approach in terms of integrating fuel cells and storage, also integrating with an existing district energy heat system for 120,000 people in Greece that it exists, and they'd be converting it. They also would be exporting hydrogen and building a 120-kilometer pipeline to do that, the Trans-Adriatic pipeline, transmitting hydrogen to Italy. So this begins to look at some of the business case opportunities with hydrogen generation. The final case study for today is shifting over to the residential side, hydrogen to the home. And there are a few test cases and experimentations going on. I wanted to point to this one. The funding has been provided. They are moving forward with this program. And it's kind of brilliant in terms of what they're doing. First, the strategy is to provide hydrogen heat to 300 homes in Levenmouth on the east coast of Scotland. And they'll be providing these homes with free boilers, heaters, appliances, cooking appliances. The participants in this program will pay the same rate for the hydrogen heat as they will for natural gas today. The approach for the infrastructure is to lay new pipes for the hydrogen and lay those pipes alongside 1,000 properties. So they're clearly expecting 1/3 of the people to participate, but it's not a requirement. certainly. So consumers will have the choice of staying with natural gas or switching to green hydrogen. The funding, you can see at 25 million from Ofgem, which is a funding resource in the UK. The Scottish government has put in 10 million, and then there's additional funding from the primary host, which is SGN, as well as 3 other of the British gas distribution networks. And you can see it's wind power to electrolysis. It integrates hydrogen storage, and then zero carbon heating for the homes. The illustration here shows from left to right how the hydrogen flows, and at the very last shows what the impacts are on carbon. The wind turbine, that's the wind turbine. It already exists. It's a 7 megawatt turbine offshore. It is estimated to produce 21,000 megawatt hours per year. I've just shown an image of an electrolyzer. I'm not trying to pitch or promote any specific company. But if you match the electrolyzer to the wind turbine and run the numbers, it would produce 429,000 kilograms of hydrogen per year based on current system capabilities. The homes, based on the heat load in the UK, the average heat load per home, would require 360 kilograms of hydrogen per year for heating each home. That's an actual home in Leavenmouth with the turbine sort of hidden behind the house, interestingly enough. The hydrogen requirement, therefore, with the 300 homes would be 108,000 kilograms a year. So what this shows, first of all, is that the turbine that they already have is provides more hydrogen than the 300 homes will provide, by almost by a factor of 4. So plenty of hydrogen production. Obviously, the electrolyzer will probably be a 1.5 megawatt electrolyzer, or maybe a 1 megawatt electrolyzer with storage. You don't need the electrolyzer to be so big going forward. If the homes are heated only with hydrogen, you have to absolutely make sure that you have an oversupply of hydrogen available at any given time. And so this speaks to the critical importance of having sufficient storage of hydrogen, especially with a small network. You don't get the benefit of the network effect in terms of modulating demand and having sufficient supply on hand. So the 300 homes, the carbon reduction is close to 1 million tons per year. So it is fairly significant for these 300 homes. Each house with natural gas would emit about 3 tons per year in carbon. And so you can see that going to a zero carbon wind sourced hydrogen strategy is fairly significant in terms of the carbon mitigation. And the final slide for today is just to show that the industry manufacturers of heating systems are moving ahead with various solutions that run on hydrogen. And I just wanted to point out there are fundamentally three different technologies at use on this slide. The first one, which is the HydroGem, is a flameless catalytic hydrogen boiler with no NOx emissions. It's a fairly innovative solution developed in Italy. Baxi and Worcester Bosch are involved in several of these test cases with their boilers. They've already developed hydrogen-ready boilers that are able to take a mix of hydrogen and natural gas. The two boilers that we're showing here, which are still pretty much on the lab bench, but getting ready for, actually have been installed in test cases, These are 100% hydrogen boilers that use flame technology as similar to existing natural gas boilers. And then and that's the same with BDR Thermia Group. They have a hydrogen boiler. But BDR also has talked about a fuel cell solution, and that's what we see with the Viessmann solution, which is a fuel cell combined heat and power. There are a number of these on the market today. They would tend to cost more than a standard boiler, but they provide not only heat from the hydrogen, but they also provide electricity generation at the point of use as well. And so there's sort of an interesting tactic that could be deployed here in terms of mitigating electricity demand in the heating season. So with that, I'd like to open it up to question and answer, and certainly assistance from Rick or Doug would be appreciated here. Any particular questions that people have?
There was one comment, Brad, that I believe you addressed, but I think because the question came up, we should address it again. Because of the efficiency of heat pumps, the suggestion was made that you wouldn't have the 4 times the electric load that you showed on the chart with the blue peaks and the red electricity load. The suggestion is that if heat pumps were used, you wouldn't need 4 times the power.
Yeah, that's a extremely valid point. Heat pumps at their best are 300% efficient, which sounds crazy. How can something be 300% efficient? But that is the case. And I think that the issue remains that in the coldest, it's usually seen as the 5 cold day strategy, which is, what are we going to do with a 5-day cold snap? How is the system going to respond? What's the efficiency of the heat pump going to be during that period? Certainly in warmer climates, this is certainly important in the United States, which is if you're in the southern states as opposed to northern states, you're the warmer states versus the colder states, the systems may have different implications. The strategy may need to be different, but that is an extremely good point. I think that what that means, certainly the modelers would have looked at that implication certainly as well, looking at what end uses were driving demand in an electric versus gas strategy. But very, very good point. Thank you for that.
There was someone noted for all of our edification that National Public Radio apparently did a story on wastewater source heat pumps. That is new to me, so I'm interested to take a look at that.
I can only respond to that because I recently did an assessment of a variety for a university, and the opportunity exists to actually put a heat exchanger in the downstream water from a wastewater treatment plant, and to use that as the ambient temperature for the heat pump system. And it does speak to there's ground source heat pumps because you have to drill a fairly significant hole in the ground, and if you're a big facility or a multi-facility campus situation, that means you're going to be digging hundreds and hundreds of wells in order to get the heat exchange. But you can also use ponds, lakes, wastewater treatment, effluent results, rivers. Europe, they're doing river source heat pumps. And I mentioned the project on the East River. So it's new to the United States, but I think we'll see this area develop going forward. the key, of course, is how much energy do you need? What's the temperature of the water, and what's the flow rate? And the calculations are fairly straightforward. And I think that what we'll see is as district heating systems develop, they'll be scavenging sources of heat, and that certainly will be one of them. Very, very good point. I'd be interested in knowing more about who was suggesting that and what their interest might be. It's a fascinating area.
The next question has to do with waste heat. It's not really a question, it's a comment. It says waste heat can be used to produce refrigeration and air conditioning using waste heat without refrigerants or outside energy. I don't know if you have any comment on that, Brad.
Innovation
How would
important.
The next question is, how would existing pipelines deal with hydrogen embrittlement? And before you respond, Brad, I'll just make a note that one of the major natural gas pipeline companies in the European Union, the second largest gas company in Europe, they said in a presentation just this week that 70% of their existing pipelines are already hydrogen ready from an embrittlement point of view. There are still valves and connections that may have to be improved, but the pipes themselves are fine.
Yes, and in the UK, they expect that 90% of all their pipelines will be replaced with polyethylene by 2030, pretty nearly 100% by 2032. So they started replacing iron pipe with polyethylene pipe maybe 20 years ago, and they had no idea that they were future-proofing their pipelines. But as it turns out, the permeation of hydrogen through polyethylene is negligible, if non-existent, and so that's been a very good sort of a stroke of luck for those systems. And so there's no question NREL is put together a group which is conducting a multi-year study of different pipes and the issues associated with moving hydrogen through those pipes. I think SoCal Gas is doing research on different pipe types. The Cumbria test site in the UK is doing testing of multiple piping solutions. So the industry is working hard. There's a great study, it's about 10 years old, but it hasn't changed a whit, by NREL on the use of hydrogen in pipelines. So that the technology and the implications are well understood. There will need to be swap outs or switch outs of certain materials. We've been dealing with hydrogen as an industry for 100 years, and so the solutions are well understood, and the challenges, but the industry certainly is addressing them.
I have two other points on that issue. One is that Linde is developing a technology. They've already demonstrated it. They're trying to scale it up that would allow us to extract pure hydrogen from a pipeline that only had a mixture of hydrogen at 20% or below, which would not be a danger to a pipeline that would be subject to embrittlement if it had a higher percentage. But you could put the 15 or 20% hydrogen through that pipe, and Linde's technology would extract just the hydrogen from the other end. And the other point that I wanted to make is that end uses in general are going to ramp up along with the improvements in the pipeline. So if you're looking at combined cycle power plants that would be getting greener by using eventually 100% green hydrogen, those plants today are not ready to burn 100% green hydrogen, but they can burn a mixture. So as the customer gets cleaner and cleaner, the pipelines will improve to meet that need.
Excellent points.
The next question is very specific. It says, Brad, do you know if Hydro-Quebec's pipeline to Portsmouth, New Hampshire is suitable to carry ammonia or hydrogen?
That's certainly a question I can't answer today. So
If anybody on the call knows the answer to that question, please put it in the chat so we can all find out. I don't know either. The next comment, shouldn't we consider ammonia as a candidate vehicle for hydrogen transport? The short answer to that is it's very much being considered, but go ahead, Brett, I'll let you comment on that further.
yes, I think it's called the most aggressive project in that. Well, first of all, there are multiple projects in that, but the most aggressive one to date is the NEOM project in Saudi Arabia, which is it's a $9.5 billion project to generate green hydrogen from solar power and convert that hydrogen into ammonia, and then to transfer that ammonia around the world to various markets. And I think the primary use of that ammonia will be to convert it back to hydrogen at forecourts used for refueling trucks as a strategy. And Rick, I know you were on a presentation on that today or yesterday. Is anything else to add on the NEOM project?
No, I think that covers it for purposes of today's discussion, Brad. Thank you.
Yes, and I think that the other thing that we're seeing is that for the shipping industry, it's very challenging to decarbonize, the marine industry. They're even looking at running turbines on ammonia on ships for propulsion. So ammonia could actually be a marine fuel going forward as a solution. And ammonia can also operate in gas turbines. And so there could be a use for green ammonia in power production as well. So we can begin to see, once we take the carbon out of our activities, we can begin to see other solutions emerging. And the search is very active for low cost pathways in order to decarbonize. I think
The next question.
Go ahead.
Go ahead.
I think we can do a few more questions, even though we've come to the end of our hour.
No one will be offended if people have to drop off in order to deal with their own schedules. The next comment / question is, why are cross-channel pipelines needed? Do economics really drive this need? Wouldn't the UK providing for itself and France / Germany for themselves be the best economics? What drives either region producing more at lower cost than the others? I have a response to that, but I'll let you go first, Brad.
No, Rick, please do. I mean, there's a lot of. I mean, right now Denmark has a way oversupply of wind power, and they ship it all off on their transmission connections to Europe, and so that could certainly help. Yeah, but there may be a lot of excess power coming into Scotland and Ireland, and and Great Britain, certainly because of all the North Sea interconnects that they have along their northern coasts, and that may drive an interest in moving that energy onto the continent. So I can imagine that is probably likely the case, and there'll be also a lot of wind power coming on to Germany and the Netherlands that need to move south as well. So you can see the need for these pipelines. And then finally, they have pipelines coming off of Africa, and there's been a huge effort. I remember this from 20 or 30 years ago, which is the idea of putting a ton of solar in North Africa and moving that power to Europe. Now, I guess we're looking at moving hydrogen from big solar installations in Africa and moving it into Europe. So Rick, go ahead.
I think this question gives us an opportunity to take a step back and realize how large an undertaking greening our entire energy economy is. Oil, coal, and natural gas supply an enormous amount of power. And despite the sources that you just discussed, which in the short term might cause the need for those pipelines going south, I think that the amount of power and the amount of green hydrogen that are going to be required to green everything from steel making to buildings to powering ships and even airplanes are going to require huge amounts of green hydrogen. And that's why we have the Saudi Arabia project and the Africa projects. These pipelines are being planned on the theory that in the long run, to meet the big need, you'll need to get hydrogen from places like Africa and the Middle East, where the solar and wind resource is huge. The next question is, does 20% H2 meet the WOBE, if that's how you pronounce it, the WOBE index requirement of most combustion equipment?
Great question. I don't have an answer to that. The test that went on at Keele University for 120 buildings of 20% hydrogen over a year did not require any change in any of the appliances, and it included quite a number of residential facilities as well as teaching buildings. So all of the equipment, certainly combustion equipment that was used for natural gas, was able to be used without any change for hydrogen. And that's kind of what we're seeing in the actual mixing of hydrogen up to 20% by volume in the marketplace. But I don't have an answer to that specific question.
The next question is, are there any direct coal to hydrogen conversion systems in research and development or already existing?
You know, coal is a source today of hydrogen, and I do not know the specifics of that process. I can only imagine that coal is being used in perhaps even in steel manufacture or coking processes, and they might be taking the syngas off of that process and generating hydrogen for other uses on those plant facilities. But that you know, I'll be frank, I don't spend a lot of time trying to understand how we can use coal going forward, but I think coal is already used to produce hydrogen today.
Make a point. I just looked up the WOBE index, and it mentioned town gas as a product made from coal. And so there is actually some effort to create this quote unquote town gas, which is more hydrocarbon than pure hydrogen. But so that's an R&D and already existing use right there.
Thanks, Doug. That's very good.
So the next question I think can be answered easily, but it says, was there any discussion of the possible dangers of methane for transportation through the pipelines? For instance, escape from pipes of storage containers. That is an ongoing problem of pipeline transport for natural gas.
Yeah, errant methane is a big issue and needs to be addressed. The petroleum industry is the biggest emitter of methane in the country, and then the number 2 and number 3 are wastewater treatment, landfills, and agricultural processes. And we need to mitigate methane emissions in all of those forms going forward. There's been a big effort to reduce methane emissions in specific pipeline systems because that's an overlooked area historically. And I think, certainly in Europe with all the pipeline replacements they've been doing, they've certainly been able to mitigate errant methane leaks. If there's a international effort that is ongoing to address errant methane leaks. I'm kind of wondering if they meant to say hydrogen in that question instead of methane, but it's absolutely important to mitigate. Methane has a higher impact on greenhouse gases per unit than carbon dioxide, so it is important to mitigate methane leaks. That should be part and parcel of any country, state, or company's activities going forward.
We have quite a few questions left. I don't know if you want to keep going, or I told people at the beginning in the chat that we will be answering all of the questions from this session and the previous 3 sessions, and we'll email those answers to everybody who's been at any of the sessions. I started working on those in the last several days. And
Well, let's
should
see if
be
we
able to
can
get
do
them
a
out in a few
lightning
days.
round, Rick.
Lightning round.
There we go. Come on.
All right, well, there's a question about blue hydrogen that, oh, I lost it here.
When will blue hydrogen be rightfully designated as that hydrogen derived from seawater?
My understanding is that blue hydrogen is hydrogen that's made from natural gas by steam methane reforming, and the carbon is either used or sequestered and therefore not gone into the atmosphere. And is that blue?
I think that this speaks to the discussion all of us have from time to time, which is why are we talking about colors, the colors of hydrogen. And this is a redesignation of blue to mean hydrogen from seawater. And it's a great point. If you electrolyze seawater and then pump the oxygen back into the ocean, maybe you're helping reinvigorate dead zones, as mentioned here. So I think that there are, for example, I think ITM Power is putting a floating electrolyzer out on a wind farm, and they'll be using seawater to generate hydrogen at the point of which the electricity is generated by the wind farm. And it was pointed out that the cost to transmit hydrogen is cheaper than the cost to transmit electricity, meaning that when you lay an electric line, it's very expensive, as opposed to laying a pipe for moving hydrogen from an offshore wind farm to land. And so I think that's enough said on that.
Tom Mikas, who's asked several of the questions a little further down, notes that coal gasification can make hydrogen. We were talking about before about making hydrogen from coal. What about NOx emissions from burning NH3?
Good question. NOx, there's a temperature. If you're above that temperature, you're going to produce NOx, and there are different amounts. So this is an issue for the turbine manufacturers. They're wrestling with this. They're putting in NOx abatement technology on the hydrogen-fired turbines, because that's a key issue, and they are succeeding at that, but it's an important issue that has to be included in any of these combustion strategies. Next.
Says, this comment, I think I know what this comment says. Hydrogen is an indirect greenhouse gas. But I think that's only true because hydrogen is currently made from natural gas. But if we're talking about electrolysis hydrogen, it would not be a greenhouse gas.
If you emit hydrogen into the atmosphere, it's got to have an impact somehow. So interesting. And it's important to know what that is. Next.
So here's the last question. Pipelines and/or packeted over-road delivery with gaseous hydrogen cells, how to direct toward individual consumer consumption, businesses, homes, automobile scale transport. There seems a need for packeted fuel cells. I'm not quite sure what packeted means, but
Yeah, I mean, as we mentioned earlier this week, Rick, there's in Japan, they're using what's the interstitial storage technology with you know, they're using canisters of hydrogen stored interstitially in rocks, and they're delivering those canisters to homes, and they're plug and play. So you have a delivery person like carrying jugs of water. They come to your house carrying these compact units of hydrogen storage, and they're basically snapping them in and snapping them out for your home heat. And it's a different kind of strategy, certainly. So I'm not sure that's what they're speaking to here.
and it looks like Tom has provided us a link to a study that's probably going to tell us something about hydrogen as an indirect greenhouse gas. So we'll all take a look at that.
Excellent. Okay. I think that's it. Well, thank you,
Yeah,
everyone, for participating in today's hydrogen session. I hope you all learned something today, and we are available at the Hydrogen Energy Center to answer any questions you might have in follow-up. And you can certainly find my contact information on the valerity.com website or the hydrogenenergycenter.org website. Rick and Doug, is that it for today?
I believe that it is. Thank you very much, Brad.
Excellent. Thank you, everyone.
Thank you, Brad.
Thanks, Brad.
Yep.